And you can see from the list of institutions on the right, I'll mute that. Yeah, there are a lot of people involved all around the country and internationally too. Now, to set a context, we've been looking at various aspects of the lunar poles over the last 4 years. And when we started, the moon wasn't actually wasn't a 4-letter word. In fact, it was allowed to have a capital M. And so at that time we were really hoping and trying to do research that helped both scientifically and for engineers the idea of going back to the pole and the moon in general. And what one often heard back then was of the moon, on the moon, and from the moon, and that's something that we tried to address. So the opening slide here is what good is the moon for exploration, and where we attack this from is the fact that the moon is a natural laboratory of planetary processes. It suffered impacts, volcanism, tectonism. It's also an excellent platform from which to observe the universe. When the vision for space exploration came out, there was a lot of discussion about the fact that it wasn't science-driven, but we contended that that actually wasn't a problem because if you really got back to the surface of the moon with people, you would have more science you know what to do with. The moon is an excellent place to conduct planetary scientific exploration. And it's also a good opportunity to use in place restructure and resources. And some of the work that we did that I will touch upon, it assumed that you were going to have some level of infrastructure on the lunar surface, and how would you make use of it? Analogous to how you can plan to do scientific exploration on Antarctica because McMurdo exists. So even though I've been very kindly given 20 minutes, there's a lot that I could discuss with the team. So I've just tried to pick some highlights and try to, but not exclusively so, concentrate on things that the results had relevance to human exploration. Now, so the initial goal for the team we had 9 sort of research tasks displayed here, as well as education and public outreach. And essentially, we were going to look at various aspects of the lunar polar environment, a lot of illumination study and volatile studies, surface characterization, and also surface science instrumentation and operations. So I want to start with a couple of those that considered volatile. So I'm hoping that this is a movie that will play. And this is Dana Hurley's work, and she's a member of 2 NLSI teams, often the DREAM team. And what you have here is a model of the L-cross impact, and the colors with the density of hydrogen that it was predicted the model would be released. And at the origin, at the 0, 0, you actually have, see if I can play it again, you have the lamp field of view. So if we go back to the slide, please. Right. So what Dana was able to do with her model was to run, you can see both the observed mass based on one of her model runs versus what they predict to be the total mass released as part of the L-cross impact. And part of how this was calculated is Dana runs a series of models bracketing a range of velocity and temperature profiles. And what you have plotted here are ones for which the model, the light curve predicted by the model matches what was actually seen by L-cross. And if you then integrate where you see colors here, you can get an estimate for the total mass of different species released as part of the L-cross data, but based on what LAMP saw as well as modeling. At a different level, Carl Hibbett led an effort working with Tom Orlando, looking at various aspects of OH and H2O life cycles on the moon. The left-hand part of the pitch here, he's been studying how solar wind can cause OH minors to be formed, and how the OH would actually migrate within grains of the lunar regolith. He's also done modeling shown by the middle one here. If you actually have water implanted on the lunar surface, say from a cometary impact, how does that water actually migrate from grain to grain within the surface, and how does that help it get buried and then protected? And finally, the third picture on the right shows part of his modeling is to work out how quickly the water can become a resource and significant amounts go down to enough depth that they're protected from future impacts. As well as doing modeling, Carl and his colleagues have done some interesting laboratory work where he can take lunar analogs here on the graphs on the left show GSC-1A and Orbite, so you have a Moray and a Highland analog, and he can place different amounts of water on the surface and then heat in a controlled environment, heat those analogs and measure at what temperature different amounts of water is removed, and thus calculate how well it's actually attached to the lunar surface. All of this, amongst other things, has led to a model of solar wind formation and loss of OH compared to observations. And what Carl and others find is you actually get most OH formed at the subsolar point, but whereas it's formed is linear with temperature, the rate that it's formed is linear with temperature, the rate that it's destroyed is exponential with temperature, which is why, not surprisingly, you predict to see more towards the limbs of the moon, which matches reasonably well with the observations. Slightly different approach, our largest engineering task was led by Jerry Johnson out of University of Alaska Fairbanks. And the problem is that the effects of different gravity, soil types, and physical processes make it impossible to actually predict machine performance using just Earth-based tests or traditional models. The whole here is to produce a discrete element model. It's the other use of the term DEM, to solve a variety of problems in space science and engineering, particularly relevant to the moon. And the idea here is if you get the microscale physics right within the model, then you can use this model as sort of building blocks to look at fairly complicated engineering tasks, and the model accurately predicts what you would experience. And some features of the DEM has been, we've over the 4 years has improved realism of the digital representation of regolith properties and processes. Using supercomputing capabilities that they have up in Alaska has allowed much more complicated particle shapes and size distributions to be used, and we deem that that's incredibly important if you're going to try and accurately predict the forces and strains that different engineering things would encounter. And the type of thing that they've done is they've tested the model by doing wheel digging and scoop digging, both percussive and non-percussive, in a lab at Ames, looking at the forces that are measured, checking that the model then predicts the same value for those forces, and now that the model is sort of been validated, you can then run the model for the type of thermal environment or vacuum environment that you can't do a physical test on the Earth. And just one more movie, because I think it's very interesting, it's been a very exciting part of the team, which just shows a quick 20-second movie showing an example of a DEM for the rover wheel. Oop. Obviously, a lot of friction there because it stopped. There we go. How am I doing for time? 10 minutes. Okay, let's go back to the slide. I can keep going. Right. So the neutron spectroscopy task, led by David Lawrence here at APL, working closely with Richard Miller at University of Alabama, Huntsville, that's a good example of how the NLSI led to some surprising results. The proposed task was to study the feasibility of basically hydrogen detection techniques on the surface using neutron spectroscopy. How would you do high-resolution surface measurements of hydrogen? And this required an enhanced modeling capability and new neutron analysis techniques. And while they found actually that part of the task that it's actually very hard to do what they had they would do, the actual model that was produced, they've actually used it to take advantage of results that didn't exist when the NLSI were formed, namely the M-cubed results showing the discovery of surface water. No one had really considered how would you detect a wet layer on top of a dry layer using a neutron instrument. And this is something that they were able to adapt their enhanced model to look at. And these results are valuable to HEOMD because they expand the techniques for resource identification, as well as a new understanding of lunar volatile processes. And Rich is going to give a talk later on in the forum. I don't want to steal his thunder, but one very exciting result that he'll go into more detail, but I was allowed one slide, is the first detection of fast neutron enhancement at the lunar poles, localized to Shackleton crater. And it may reveal, enigmatically referred to here, the newly detected hydrogen stratigraphy. So John Grant at the Air and Space Museum, the Smithsonian Institute, was looking at using ground-penetrating radar on Earth for a couple of reasons. One shown here is taking GPR measurements of planetary analog sites to try and determine how well could you use GPR on the lunar surface to get subsurface stratigraphy. So they took a bunch of data in around Meteor Crater. This was facilitated by another LSI member, PI David Kring, and they used the GPR at two different frequencies, 400 megahertz and 200 megahertz, and they determined that the 400 megahertz worked better, not surprising because it could penetrate sort of further. Did a very good job at measuring the block distributions at about 1 meter depth. And what I suppose Meteor Crater is quite handy is because it was essentially an active mine for many years, there are places where you can actually, there are drill holes, there are sort of shafts where you can go down and actually see what the subsurface block distribution is. So what John and Patrick were able to do was to measure what the actual block distribution is by looking at these cuts and then see how it compares to the GPR. The other thing that they did as part of their GPR study is this figure shows what think of it as GPR signatures from 3 different terrains. You've got ejecta in the top for Meteor Crater, you've got a pyroclastic flow, a sunset crater, an RR flow, and you've also got a sort of a equivalent of a mare, Columbia basalt. And these are quite different. And the goal of doing this is if you go, you can actually sort of build up a library of what different planetary terrains look like in GPR. So that if you had GPR on a rover on the moon, you could see what you saw as you were moving along, and you could potentially determine when you could see, it would help you provide geologic context for what you were, particularly subsurface. Jeff Fletcher here has done a bunch of interesting stuff. So one is constraining the lunar chronology. A key here is he found that measuring between crater counts around small craters, he could see that different crater densities of units that should be the same age. This has been interpreted by Heisinger and van der Bogart as different material properties, but Jeff thinks it might be something different. It might actually be self-secondary. And if it's self-secondary, that's interesting because it means that the flux for these regions is actually less than what you get from the measurement, which means they are in fact younger than have currently been calculated, and that affects the key part of the aging, the crater count age curve, which is where it's most unknown. He's also found impact melts in craters far smaller than it deemed possible from the physics that you have enough energy to actually form melts. It's only observed only in fresh craters, and it's actually rare. And he thinks that it might be indicative of a vertical impact. So it potentially helps provide more information on the nature of which impacts are vertical and which are oblique. The other interesting stuff Jeff's done is he's actually found some of the old Soviet hardware, and this is not just for grins. No one knew where Lunar Code 1 was, and Jeff managed to find it, give those coordinates to Apache Point, and so now they were able to find it with a laser, and so the Lunar Code 1, which is up here, which is in the top left-hand corner of the moon if you look at it, so it greatly broadens the range area on the moon that is covered by the network of laser reflectors. And I'm going to go a bit quickly now. Bill Sparks and others came up with an interesting idea about the moon is actually an excellent place to study the Earth to determine that the Earth does in fact have life. And that sounds like an odd thing to do. But the goal here is, what sort of instrument would you want to develop to test techniques? So how do you determine that the Earth has life? And then you can take those techniques and apply them to looking for exosolar planets. And the moon is a great place to do this because you get the full disk Earth, which is something quite hard to do from space. And also you see the Earth over a full range of phase angles. And a key here is to use polarimetry, because terrestrial planets are polarized, whereas stars aren't. One collaboration that came about part of NSI that wasn't planned was actually working with the L-Cross team to analyze some of the Earth imagery they took when L-Cross was doing its 2 looping orbits around the Earth. And the highlight of this was the ozone signature at the near UV, which is due to life on Earth. I'm going to go through this one quickly. The Illumination Study, we were very fortunate during our time that the topography information was vastly improved than what it was 4 years ago, both from the Kaguya mission and from the Lola on LRO. And this image here, done working with Andy McGovern and Josh Cahill here at APL, the left-hand images show simulations and the right show Clementine images for 2 very different sun directions. And essentially, we now have topography of good enough quality that you can run simulations and trust the results. And I'm going to skip this one. There we go. So what's key here is we now can essentially fully characterize the illumination conditions of a point on the surface. So you've got the maximum single period of illumination. We know there are several places near both poles that are lit for several months at a time and based around midsummer. So these are great if you want to do a mission that lasts several months. Similarly, we can map all eclipse periods, so an exact shadow location. So if you want a mission that lasts multiple years, we can help find a location which minimizes the amount of shadow you would have to encounter. And we can also look at the effect of mass height, which is something you can't do with imaging analysis, you need to do with simulation. And I'll leave you with something that Paul Spudis has done working with Tony Lavoie, which essentially come up with an affordable lunar return architecture. And the idea here is to use small incremental steps using realistic launch vehicles as well as realistic budget to build up infrastructure at one of the poles where you make use of the volatiles that's there as a first step into building up a proper deep space human capability. And I've put the paper here from the Spudis and Lavoie paper. Anyone wants to go and look at it. It's a bunch of small missions, very doable steps. I can't think of a better slide to finish on than essentially what you might need to do to go back to the moon. Thank you.
Thank you so much, Ben. That was great. Really appreciate it. We've asked for people to start typing in their questions, but I don't see any in there yet. I noticed that you skipped over one of your movies, and I was wondering if while they're typing in, it looks like Clive is typing, maybe you want to show the Kaguya movie if it's easy to do?
Yes. Oh, if Clive is typing, I'll definitely distract him. So this just shows an example of once we realized we had topography that you could trust. It just shows actually simulations of the South Polar region for a whole year, so 12 lunar days. But from the simulation, now, when we do these simulations, we put on sort of a Lambertian cosine brightness, so it looks like the moon. Whereas when we're doing the analyses, we sort of churn out binary images, which is basically lit or dark. But we can also determine when you're looking at partial sun, which can be key if you want to consider what power generation capabilities you might have at a point. And this, one thing that this work did lead to is a lot of collaboration, both within the States and with the European Space Agency, where we were able to try and help potential future missions.
Okay, great. And it looks like Clive finished typing. He says, what about the results of the radar experiment and Arecibo? Did I miss that when there was no sound?
No, Clive, that's actually, this talk is my LSI results. Actually, Wes Patterson is giving a talk where he's going to talk about some of the bistatic measurements we've been taking with Arecibo and Mini-RF.
Okay, and Okay, let's take this one from Chuck Wood, and then the rest I think you need to take offline into the chat room. Chuck says, your slide said there were some permanently shadowed areas as far equatorial, I think, as 58 degrees. Is earthshine an issue for maintaining low temperatures?
No, one of the, yes, I sort of went to agree. One of the surprising results is we thought, hey, I wonder how far from the poles you can still get permanently shadow, and we found that the answer was 58 degrees. And yes, as you go further away from the poles, it does get warmer. I don't think it's from earthshine, it's more from the reflected light. But this is actually interesting because there is some discussion that you don't want to be as cold as possible because you want the volatiles, if they're too cold, volatiles on the surface are stuck there, whereas you'd like them to have enough energy to migrate into the surface so that they're protected if you want long duration resources. So in fact, some of these non-polar permanently shadowed regions might be interesting because they are slightly warmer.
Okay, very good. Fascinating. Okay, and if you would go into the chat room and answer your questions from people from here on out.